Hello guys, welcome to another video. This video is going to be the walkthrough for Ethernaut switch. The objective of this challenge is quite simple. We have to flip the switch on. How we're going to achieve that is there is this variable which is called switch on, which is false by default, which is off. We have to turn this variable to true to finish this challenge. So before seeing more of the code, let's just copy this code into Remix to go to the code review. So just paste the code here and let's get into the code review. So we know that our primary objective is to turn this variable to true. So if we go through this contract to find where this is manipulated, this variable is manipulated at two places. The first one is this turn switch on function, which seems very straightforward, which sets this variable to true, which is our objective. But there is the problem of this only this modifier. So what this modifier does is it has a require statement, which requires the message.sender to be equal to the address of this. So which means that the caller of this function should only be address of this. So it is essentially an internal call. It can only be an internal call where the message.sender is going to be the function itself. So if the only this contract can call this function, let's look at the other functions that are available. So there are two other functions. The one is this turn switch off function, which is the same as this turn switch on function, except this turns this variable to false. And there is this one last function, which is flip switch function. It takes in bytes data, and what it does it calls this address, this contract's address with this data. So from here, the objective seems very clear. So what we have to do is we need to get the function selector of this turn switch on function and input it as the data, and our objective will be completed. But here also there is the problem of this modifier, which is only off. So if you look at this modifier, first we declare a variable which is the selector, which is going to be a bytes 32 array of size 1. Then we have a one-line assembly code which has this call data copy function, where the inputs are first there is the selector, which is the variable we have declared, then there is 68 and there is 4. To understand what this function does, we need to go to the whiteboard. So let me open up the whiteboard. Okay, so we have this function which is called data copy, and it has three inputs, 1, 2, and 3. From what we have seen in the function, we know that the first one was the variable that we have created, and the second one was 68, and the third one was 4. And before I dive deeper into this, I want to be assured that you guys know the fundamentals of Solidity assembly code. As you have previously gone through all the challenges in Ethernaut, that's why I'm only focusing on this specific function rather than having an overview of Solidity assembly. So I strongly recommend you guys to go through Solidity assembly before coming down here. It's a short topic and it should not take much of your time. So now that's away. Let's start looking specifically into this call data copy. So from the name of call data copy, we can infer that this copies the call data. So it copies the call data. So we should be having this question of what is call data. And if you don't know what call data is basically a hex value which is passed in the function call. So passed in the function call. So what is this value going to be? So the call data is a hex value which is going to be first the function selector plus the inputs of the function. So So the hex value is going to be like this. So 0x and some value. And first it is going to be consisted of the function selector and then the inputs of whatever the function it is. So I will dive more deeper into the structure of call data in a short while. But for now, all we need to understand is that the call data is a hexadecimal value and it is the function selector plus the inputs of the function. And now coming back to this call data copy, we infer that it copies the call data. So the first question we should be having whenever we are copying is to where we are copying to. So to where. So the first question is answered by the first input, which is our variable. So we are copying the value to our variable. And the second question should come is from where. So from where. Here the answer is obvious, which is call data. We are copying from the call data, but here it is more specific to the position of the call data. So the second variable is actually the uh, position. So we know that the call data is this hexadecimal value, which is going to be going, and from this whole call data, we are specifically taking the position from the position 68. And coming to the third question we should have is how much. So how much simply means that the size of the how much size we are copying from the call data to our variable, and it is the third input, which is 4. Here the size is expressed in bytes. So for now we have this basic understanding that call data copy has three inputs. The first one is going to be a variable to which we are copying the value from the call data, and the second one is going to be the position of in the call data from which we are copying from, and the third input is going to be the size of the hex we are copying. So the size is which is basically 4. So now we know the basics of call data copy. So let's go back to Remix and look at the rest of the code. So after this assembly code, there is this require statement, and the it requires that the selector of position 0, which is the variable that we have created, and what is stored at this slot is whatever we have copied from the call data, which is from the position number 68, and the 4 bytes after it are copied here, and it requires that it should be equal to the off selector. So if we look at the off selector, it is actually the bytes 4 of the hashing function of turn switch off. So the turn switch off is this function which turns the switch to false, and we are loading the function selector of this function here, and the and our call data which we have copied should be equal to this function selector. So for now we understand this this modifier requires that in the call data the position number 68 and the 4 bytes after it should be equal to the function selector of this turn switch off function. So to bypass this condition, we need to first know the layout of the call data for this function. So there are different ways to know to view the call data. For now, I'm going to use Remix itself, and for that, first let's deploy this contract. So I'm using the Remix virtual machine, and I have deployed the contract, and we can see the flip switch function, which requires the bytes in data. So originally, when we viewed this function, we saw that this calls the function inside this contract. So there are two functions inside this contract, which is turn switch on and switch off. So our goal is to call this function. So we need to get the function selector of this function and give this as the input so that this function is going to call this function. So for that, we need to get the function selector. So we can see that here we get the off selector. So let's duplicate this line and let's call this the on selector. And you can see that the name of this function is turn switch on. So let's save this contract and deploy this once again. And now we have the on selector. Let's copy this and paste it right here. And let's call the flip switch function. So here we can see that the function has failed. We know that it could fail because we have not yet bypassed this modifier which is only off. So for now, let's view the call data. So here you can see the field of input. This is the actual call data. Let's just copy it and let's paste it here. And, okay. Okay, now we can look at the whole bytes value and we can notice a lot of empty zero values. But if you look, there is this value at the beginning, and then there is this value, and then finally here are a bunch of values. So previously, we saw that the call data will contain the function selector plus the inputs. So coming to the first value here, Uh, I hope you guys know that two hexadecimal values correspond to a byte. That is because one hexadecimal value can contain 16 values, and a combination of two hexadecimal values, 16 plus 16, can contain a combination of 256 values, which is going to be 8 bits, which is going to be 1 byte. So if you guys can count, here are 8 hexadecimal values, which is going to be 4 bytes. So these 4 bytes are actually the function selector. So these 4 bytes are the function selector for the flip switch function. So this is the function that we have recently called, and this function selector corresponds to that function. So we are done with this first part. Then next we have this input. So if we look at the rest of this hexadecimal value, we can see the number 2 which we didn't give as input, and here this 4 also we didn't give as input. But if you look closely, this value is actually what we have given as input. 76227012 is actually the input data that we have given to this function call. So we understand that this part is the input, but what are the remaining 2 and 4? So to understand the remaining values in this call data, first we need to understand the difference in the call data structure between static and the dynamic values. So to understand them, let's look at an example. And for that, let's get down to Remix. And here I'm going to create a simple function. Let's call this simple itself. And this function is going to take an input as a static variable. Oh, and I hope you guys know what is the difference between static types and dynamic types. So if you guys don't know that, the very simple explanation is that static types are those variables whose size is determined during the compile time. So for example, here is this UN256, which can take the size of only 256 bits. This is going to be 32 bytes. So the maximum size of this variable is only going to be 32 bytes, and its size is known. In contrast, if we look at our flip switch function, our input data is in the form of bytes. So this is a dynamic type instead of a static one, whose size we cannot determine during compile time, and only when we give the input we can know the size of this type. So there is a difference between these types in the call data. So to understand that, first let's look at the static types first. So let me name this as number one, and also another event 256. Let's call this number two. It's a public function. Let's keep it pure. And then there's going to be this another event 256, which is going to be number three. And let's have it number one plus number two. So we have this simple function, and let's deploy this contract. Let's deploy this, and here's the function. Let's keep the values simple as 1 and 2 for the function. And here, let's copy the call data. So as seen previously, the input is going to be the call data. Let's copy it and paste it right here. And then also format it, make it visible. Okay. And now we can see this value. It looks quite similar to the first one. So first we have this function selector. It's a function selector to the simple function. And then as we know from the previous slide, we have the function selector plus the inputs. And this is a function selector, and the input we gave were 1 and 2, and both of them are here. Unlike the previous one, here all the values that are present in this bytes are the values that we know. But you may have the question of why there are so many zero values. That is because of the arrangement of the call data. So call data is arranged in a way that first there is this 4 byte value for the function selector, and then all the input values are stored in slots of 32 bytes mostly. So 32 bytes and 32 bytes. So as I previously told in Remix that the static variables such as uint256, so let's write it, uint256 is going to hold a 32-byte value. So for now, this is just a number one. Imagine if it were like 100,000. So this value, the maximum value is going to be 32 bytes, and it will be allocated 32 bytes. So if you could count here, the 8 byte ends. So here it ends. So this is going, oh, sorry. So here the 4 bytes end. So this is going to be 4 bytes. And after this, if you could count till here, this is going to be 32 bytes. And then till here, this is also going to be uh, 30, 32 bytes. So for the static variables, this is very simple. First, there is this function selector for 4 bytes, and then each slot there is the variable that has fixed size, which is going to be 32 bytes. Now let's understand the dynamic types now. Let's now go to our actual value, which is this call data value. So from our understanding, we know that this is the function selector, and then there are 32 bytes slot. Here also there are 32 byte slots. So if you could count, this is the first slot for the 4 bytes, and then here is the 32 byte slot, and here is the next one, and here is the final. So for now, for this call data, there are actually one function selector slot, plus there are three slots of variables. So three 32-byte slots, and the values in here are the first one has 20, the second one has 4, and the third one is actually the int. So now let's get to the how the dynamic values are structured in the call data. So the dynamic value has two parts. So a dynamic value has two parts. One is going to be the offset, and the next one is going to be the data. The offset is actually the first value. So for the first input, so this is our input, right? So this value is our input. So in the call data for the first input, after the function selector, the first slot. So this slot is going to be the offset. So what is offset? So offset is the location of the data. Location of data. So why do we need the location of data? So because our dynamic types does not have a fixed size, they can span across multiple data slots. So that's why we need to know where the data starts from, so we can copy the data. So the first slot we have identified is the location of the data. So what is this value 20? So this 20 value is actually in hexadecimal. It is a hex value, which means that 20 in hex actually corresponds to 32 in numerical. So here 20 means that from the start of this slot, which is here, this is the start of the slot. After 32 bytes, the data part will start. So according to our value 20, the data part starts right from here. So here the data part starts, and the data part also consists of two values. The first one is going to be the size of the data. So here this 4 is there because it is the size of the data. So what we have given the as input is this value, which is the function selector for the turn switch on function. So our input was 4 bytes and it is given here as 4. So this 4 is the size of the data. And the next part is the actual data itself, actual input. So this is the actual input which is starting from here and it ends here. So normally our values are padded to the right and the function selectors are padded to the left. So you can see the number 4 is padded to the right end of this 32 byte slot and our function selector is padded to the left side of this 32 byte slot. It is because Solidity is programmed to be in this way. So now we understand each and every value of this call data value. So from our call data copy function, we saw that call data copy had the input of the location as 80, oh, sorry, 68. So here the location is mentioned as 20 and here it is 68. So here it is mentioned as 20 because it is in hexadecimal. This 68 is actually numerical in bytes. So if you guys can count from the start, so let's count together. So this is going to be 4 bytes, right? And then the next slot is 32 bytes. So 32 plus 4 is going to be 36. And then here till 4 there is another 32 bytes. So totally it's going to be 68. So 68 means in the call data copy is that, so from the 68 byte we are copying 4 bytes. So that means in our call data copy from this location, let me clean this up to make it visible. So 68 means in our call data copy is just from here till 4 bytes. So 1, 2, 3 and 4 bytes we are copying. So this is actually what we are copying in our call data copy function. So with this, we understand everything that we need to know. And from here, we need to engineer this and modify this to bypass the require statement. Now let's get to Remix to view our objective. So this modifier requires that at the position number 68 of the call data, uh, it should be the off selector. So it should be the off selector. So currently, if we look at our this version of our call data, version number 68 is actually here, which is the on selector. So we need to modify this to be the off selector to bypass this modifier. So first, let's do that. So let me uh, copy this and paste it at a new location to make it more visible. So To make this easier, let me separate this by the slot. So here, this is the first slot for the function selector, and then here is the next 32 byte slot, and here is the final 32 byte slot. So this is going to be the start of location number 68, which is in bytes. So here, this should be the of selector, of function selector. Let me go here to grab the op selector. First, for that, let me deploy this. And here, so let me grab the op selector, which is this value. So let me paste this value here. So this value is the op selector, which is at position number 68, and this should be always here. This is the condition. So by this version of our call data, we have bypassed this modifier, but still we have not reached our goal. So our goal was that whenever we call this flip switch function, we need to call turn switch on function. So by this version of our call data, what we are doing is we are calling this turn switch off function. So we need to modify our call data so that we are calling the turn switch on function, but also keeping in mind that we should never change this part. So the location number 68 should be this turn off selector, but our call data should call the turn switch on function. So we can't modify this part of our call data, but we can add to our call data because this is our call data and we can directly use this to call our contract. So let me, duplicate this again and add the on selector also. So let's go to remix and then let's get the on selector. And now let's add the on selector to here. So we have the off selector at position number 68 and we have the on selector after that. But still, even if we call the contract with this call data, it is still going to call the turn off selector because of our offset. Our offset is set to location number 20 in hexadecimal, which is going to start here, which says the length, which is 4, and it is going to call this function. So only just by modifying our offset, we can redirect the function to use this input, while this value stays the same. So what we need to do for that is, first we need to have the size of this input. So this input is also a function selector, which is going to be 4 bytes. So let's add this 4 bytes. So 20 from this location is going to start from here. So 20 means 32 bytes in numerical and it is one slot. So this slot is the 20 means this slot is going to be 40 and this slot is going to be 60. So this is the slot from which our data part of our input is going to start. So we need to change 20 to 60, which is going to be the location for the start of our new data, which is our turn switch on function. So then when it reads the data, it is going to see that the length of the data is going to be 4 bytes and it is going to read this 4 bytes and call our turn switch on function. So let's just connect all these values. Okay, and the final byte. So this is our final answer. It consists of this. Oh, also I forgot to mention that this 4 is here, right? This 4 currently is a dummy value. So you can have any value, you can even have 0, and this is not going to impact our call data. Because when the function starts to read this, it will first read that 60 here and directly jump to the position number 60 and it will skip all these values in between. So whatever you have here in both these slot does not matter. And here we have the function selector for the off selector because of our required statement. So let's just copy this call data. And there are different ways to use the call data to call the function. You can use Web3.js or Ethers.js, but I'm directly calling it using Linux using this low-level function. So let's just paste it here and call the transact. And it says that fallback function is not defined. So what we can simply do is we can create a fallback function and external function. So for your version deployed in using MetaMask also, you can just create a fallback function like this, and you can give in your address, and then you can do the same procedure. So as I have added a fallback function now, I can click transact, and the function will go. Oh, sorry, I need to redeploy the contract. So let's redeploy with the fallback function, and then let's paste the call data again, and let's call transact. So our function is successful, which means that the turn switch on is turned to true. So yeah, that's it, guys. I think this video was very long. So if you guys earned any value from this video, so give us a like and please subscribe for further videos. Thank you.